Okay. So you'll see your first example of a Laurent series already today. So this is lecture 16. And if you recall, we had a definition theta x q equal to the product k going from 0 to infinity 1 minus x q to the k 1 minus q to the k plus 1 over x. And this we could write as in our q notation as q by x q infinity. And this was for now we know it's for absolute value of q less than 1. This is always convergent. Okay, and x is not equal to 0. So by a theorem of complex analysis, this can be expanded into a Laurent series around x equal to 0. I mean the basic trick I don't know, is everybody taking complex or nobody's taking, is there somebody who's not taking complex?
I'm not taking the course.
You are not taking the course. So, well, so what one can understand from all this through is that um, right now you don't worry about things like convergence. Okay, so if you look at my the examples in Sage, we are basically when we are looking at infinite series, we are basically going till about 100 and then stopping. And the reason is that when you have q raised per some power or x raised per some power, if you're only limited to some finite number, then we don't need any convergence. So we just do it, right? So you understand the things formally. You can understand the things formally by just saying, okay, I'm just calculating the coefficient of x raised per n on both sides. Okay. I'm not bothered about the convergence and so on. So then everything makes sense, actually, as far as combinatorics goes, because what in combinatorics we are only bothered about. So, but still, I mean, one can sort of get familiar with some theorems because they are needed at some place or the other. Okay, so even if you don't have any idea of what was happening in terms of when I mentioned this, just look at things combinatorially. And in fact, Euler and Jacobi and all, I mean, I don't think they were bothered too much about convergence and all that stuff. So this is just a modern day, affliction of being very, so you have to be sure that you are correct and therefore proof and so on. But, again, it's going backwards to where you're saying that, okay, I mean, I know for a fact that on a computer I can check as many terms as I want and it is correct. So why bother? Or bother less in some sense. So for discovery, which is the important thing, you don't need to bother. And in any case, a very brief, um, I can summarize complex analysis very briefly and say that there are these. I mean, so you have power series, which are these nice functions, right? They're infinitely differentiable. And then there is this major theorem which says that if it's a differentiable function and it's bounded, then it's compact, then it's constant. That means it's not very interesting if it's bounded. So it has to be unbounded in a domain. So now, then there is this thing that if you restrict the domain to some compact set, then it will be bounded because it is differentiable, continuous, it meets its bounds and so on. So again, this is not very interesting. So what is interesting is when there is a pole, when it's not bounded. When it's not bounded, that means that instead of every term being defined, there are some terms which are like 1 over z. So there will be terms like 1 over z, and at z equal to 0, it's not defined. So you could have 1 over z minus 3. So at x z equal to 3, it's not defined. So this is a pole. And the real interest in complex analysis is the when they are not differentiable in some sense always. Then this whole story starts playing out. So the poles do a lot to determine the things. Poles and zeros are essentials here. So, and there are these wonderful theorems, like I mentioned last time, that if you have a polynomial and you have certain zeros, you can pretty much write down the polynomial. And if you have an analytic function which has zeros, all zeros are known, you can write it down as a product. So these are some nice ideas which are there in complex analysis, but we don't use them much, but we need to. I mean, it's okay, you can just play around on the computer and figure out if it suits you. In any case, so what we know is that this can be written as a Laurent series, and so if so this theta x q can be written as this product can be written as something of this form. It's not z, it's x. Oh, it's n, going from minus infinity to. So that's wonderful. You are able to write it like this. So what? So, but what you do is you replace x by x cube. So consider this guy. So if I replace by x cube q infinity, and over here I'll get 1 over x q infinity. So this is, this is 1 minus x, 1 minus x cube, 1 minus x cube square, and so on. This is 1 minus x cube. So if I multiply by x, 1 minus x, and I also divide by 1 minus x. So this part will become xq infinity. And same thing, this is 1 minus 1 over x times 1 minus uh, q over x times 1 minus q square. So so there's an extra term here. And if I remove that, I will get q over x, q infinity. So this top part becomes xq infinity times this. So what do you get? You get theta xq. And this is x minus 1 divided by 1 minus x. So a lot of things cancel. You get 1 over 1 minus x. Is that clear? This did not require any complex analysis. Is that fine? Okay, give me a sign of life when I say, is that fine?
Professor, how are we getting the 1 minus x? Are we multiplying and dividing by 1 minus x?
No, the first term here is 1 minus 1 by x. The second
Yeah,
term is 1 minus q by x and so on. And then 1 minus q by x and so on is covered here.
right.
So I just
No, Professor, I
explained.
was asking on the left hand side. Are we just simply
Yeah,
multiplying and dividing?
left we are multiplying and dividing. Yeah.
Right. Okay.
So we get this. That's fantastic. So what does this mean? This means that I can bring the x on that side, and what will I get? I will get summation an, and now I'm replacing x by x q raised per n, and I'm multiplying by x and going from minus infinity to infinity. And here I'll keep the minus sign, and I have an x to the n going from minus infinity to infinity. So from this equation, right, we get this. Is that okay? It's fine. So in fact, why am I keeping the minus sign? Let me just move it that side. Now we compare. So coefficients of x to the n on both sides. What do we get? So here it's x to the n plus 1. So I'll have a minus sign, and if I compare, so I'll have a n minus 1 here, and then there is a q raised per n, and this side I'm going to get just a n. Yeah, so why not write it the other way around? So a n is equal to minus 1 q to the n. Well, I'm taking n minus 1, so it should be n minus 1, a n minus 1. Is that okay? This doesn't
Yes,
require any complex
Yes.
analysis. So, all right, so what's the next step? You do q raised by n minus 1 plus n minus 2 and replace a n minus 1 by that. So this is there. And keep going on until you get a0. So what will you get here? Minus 1 raised to the power n q raised per, so n minus 2, and then 2 here, so n minus n here, and this is n minus 1 plus n minus 2, and it will keep going on till you get n minus n, which is 0. So you get minus 1 raised per n and q raised per n choose to a0. That's okay? It's fine?
yes, Professor.
Okay, so now where are we? Where we are theta xq is equal to a0 times minus 1 raised per n, q raised per n choose 2, x to the n going from minus infinity to infinity. So, I mean, you can do the same game for both, I mean, that you have to verify. Verify, I mean, just think it through. So, n could be negative. Because we are comparing coefficients of x to the n, and n could be negative too. So here, I mean, the logic stays the same. It goes to n minus 1, n minus 2, up till whatever. And here, this negative number, so you may get minus n minus 1 over 2. So there may be some stuff here which may change. Okay, but you'll still get this. So I should just say that n choose 2 is equal to n into n minus 1 over 2 here, even when n is less than 0. Okay. All right. So we've reached here, and to find, I mean, the problem to find the complete expression, we need to figure out what is a0. All right. So we just need to find the constant term, and then we'll know the Laurent series expansion. Okay. I mean, this is not. I mean, this was done by Jacobi and Gauss, and they didn't know any complex analysis either. So don't worry about it if you're, uh, if you, complex analysis really started with Cauchy. That was much later. Anyway, so where are we? So we have to figure out this guy. I'll just write out again. So this is x q infinity and q by x q infinity, and let me write it out. So And what I want is the constant term. So which term is a constant term? So I'll pick some terms here. I pick some terms here and I pick some terms here. So here I'll pick up, let's say, A1, A2, A3. Let's say I take R of these factors. Okay. Then I have to take R of exactly those factors, right? I have to take R here so that X and 1 over X cancel. Then only I'll get a product term. So let me put it this way, that we want constant term of theta xq is made by terms such as, so what are the terms such as, what are those terms? So there are R of these, exactly R of these. So q raised per, let's say b, let's call it a1. I'm doing this first. A1 plus A2 plus A3, so on up till AR. And then I take these guys, B1 plus B2 plus BR, right? And what are the conditions? Well, they are distinct. So A1 is bigger than A2, is bigger than A3, and so on. And these A's have got to be bigger than, they're strictly bigger than 0. But these B's which are coming from here, so B's come from here, right? And A's come from here. So B1, B2, B3, BR, and this is allowed to be 0. Yeah.
Professor, why do we need these strictly bigger in air?
Because I have Q, Q square, Q cube. I want, I will have whatever, this Q raised to the power some term will be there, right?
Oh, so A is for the sec. Okay, 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 okay.
A is
Got
from the
it.
second guy and B is from the first guy,
Okay, Professor. Yeah.
right? So this is fine.
Yes, Professor. Yeah, it's fine.
So essentially, what you're going to get is you're going to get the constant term is q raised to the power, uh, let's say whatever, this plus this. So summation ai plus summation bi, right? You'll get this, and then where a's are of this type and b's are of this type, right?
Professor,
Yeah, yeah. Right.
shouldn't the sums be equal? Sum of AIs and sum of BIs.
Yeah, yeah. So I mean, whatever the sum of no, no, the sum need not be equal. The number of r's have to be equal. So I have to cancel the x's. I
Oh,
don't have to cancel
yeah,
the
yeah.
q's. So I could
Okay,
have
got it.
1 plus 5. That's 2 coming from here, and then 2 plus 7 coming from here. And when I multiply by q, I'll get q raised per 6 plus 8 plus 7, 15. And then I collect all the guys together, and I'll get something which adds up to 15. And what is that? That's a partition, right? So anyway, my claim is, the claim is such a sum, number of such uh, pairs bigger than 0 and b1 strict. So these are distinct, but one of them can be equal to 0 is equal to the number of partitions of n. So therefore, if this is true, this means The constant term is the generating function of partitions, which, as you know, is QQ infinity. So
Of n, Professor.
partitions of all n equal to the number of partitions of summation ai plus summation bi, say. And since I said okay, now it's fine. So yeah, so how do I do this? So there is something called Frobenius notation, proof of claim. For partitions. So let lambda be a partition. So let's see. This guy is lambda, let's say. Then what I do is I take all these guys. I take this guy, this guy, and this guy. And then I take these people. Let me choose another color. How about this? Okay, so for this partition, whatever it is, there is, let R be the length of the longest diagonal. We had done something called a Durfee square. So it's the side of the Durfee square too. So this 3 by 3 business, the largest square, right? Let this be called A1, this be called A2, let this be called B1, this be called B2. So let A1 bigger than A2, so on, bigger than AR, and equal to 0 is allowed. And B1 bigger than B2, BR bigger than equal to 0, be the uh, what should I call them? Arms and legs for each R. Okay, so each lambda corresponds to this array A1, A2 up till AR, B1, B2, BR with sums for some R, for some fixed R, right? So and is a partition of what? Partition of the R, these yellow guys, partition of n equal to R plus the summation AI plus summation BI. And vice versa, if you're given such an array, you can put the arms and length. So now, why are they distinct in size? This is just the only thing to be clear about. So if you have 1, 2, 3, 4, 5 here, and if you had 1, 2, 3, 4, 5 here, then you will get this second one will become bigger than this. So it has to be smaller. It has to be smaller. This has to be smaller if you're talking about, and you're allowing 1 0. Like this third one is 0. There's nothing on this side, right? You're allowing 1 0 for both these guys, right? If you had b equal to this guy, then this would be b3. That's allowed. But always you notice because of this diagonal and below diagonal business, the second guy cannot be as much as this guy because there is a difference of one already built in from this guy. There's a difference of two already built in here, and so on. Any queries? Now
So I
back.
don't follow how are strictly greater than zero as we require them to be.
Uh, Here they're greater than equal to. Here they're strictly greater. You don't follow it here or you don't follow it here?
Oh yeah, no. So we haven't connected the two yet, right? Like how both of them are
Not yet,
equivalent.
not yet, not yet.
Okay, okay, okay.
So the proof of claim is clear, right? This pair, so it corresponds to the Frobenius partition A1 minus 1, A2 minus 1, and AR minus 1, B1, B2, BR. And of course, the it's a partition of R plus summation AI minus 1 plus summation BI, right? And now bring back the R inside that summation AI plus BI. So each of these pairs also correspond to a partition of N. Okay. We do bigger than equal to 0 because this is the standard for Frobenius. If I had started with Frobenius, then there would have been no problem. But I was just motivating the fact that why it's needed. Okay, so so what does this tell you? That tells you A0 equal to 1 over QQ infinity, and therefore theta xq, which is xq infinity, q over xq infinity is equal to 1 over QQ infinity summation an q raised per n choose to x raised per n going from minus infinity to. So theorem, this is called Jacobi triple product identity, and this is due to Jacobi, as you might have guessed. It's in 1829, and also Gauss independently did it. And he published it much later. And why is it called triple product identity? Because we can bring this other product to this side. Sorry, this an is already determined. It was minus 1 raised per n, q raised per n minus 2. So this is again, I remind you where n choose 2 is just short form for n into n minus 1. Okay, and proof as above. Proof is done. Any questions? So you must be wondering when I wrote all that analysis down that where is the combinatorics coming in? It came in a very unexpected way. In 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 the constant term of this hugely complicated business. And indeed, there are many complicated formulas. Integrals. There's that where you have a constant term, and that constant term is essentially some combinatorial object. And it's not so easy. I can bet you that Preetham doesn't know this proof of finding the uh, constant term. It's not. It's not. So combinatorialists have their ways. So analysis guys will have another way of finding. Uh, Everybody has their own trickery, but this is a very sweet way of finding a constant, finding the ANs. So any questions on this so far? So this is a fundamental theorem of Jacobi wrote a book called Fundamenta Nova or something like that. So this is a very fundamental number theoretic result, and this business right here is it? Yeah, this business right here. This is known as I can write it over there. If I remember it. So this thing theta of x q equal to um, minus 1 over x theta of x cube is known as quasi periodicity. Yeah, Shivam, you have a question?
Professor, I think we are missing minus sign there above in the identity. Could you scroll up? Yeah,
Where?
there. Yeah, I think here minus should be minus. Yeah.
Okay. Now it's okay. All right. So this is known as quasi periodicity, and let me take a minor trip again. You have to stop. Don't bother to listen if you don't want to. Uh, so so this is a, I would say, you know, uh, what should I say? This is a diversion. So you have this sine of x plus 2 pi is equal to sine of x, right? This is known as periodicity. And people asked, can we have two periods? So there is a whole class of functions called elliptic functions, which are two periods. So to tell you the truth, nobody elliptic functions were like in Jacobi's time, right? And nobody bothered when they said it's all done, over, dusted, this, that, whatever. This was a story when I was doing my PhD. People said this is classical math and it's all very beautiful, and we used to do it in calculus and all, do some identity. So like trigonometric identities, there are a lot of elliptic function identities. We used to do it, it was all beautiful, and then we used to forget about it. And then something happened incidentally. At the time I was doing my PhD. So I was doing my PhD in 90s. So I got my PhD in 1995, and then there was an email which was floated. An email came. So at that time, email was there. There was not so much, the internet wasn't there. There was some kind of an internet by text written, but people used to send stuff by email, and an email came. So there was an email, maybe in 1994 or 1993, sometime like that, which said that there was a guy called Andrew Wiles. Have you heard of him? Have you heard of Andrew Wiles?
Yes, Professor. Yeah, yeah.
So there was an email which said Andrew Wiles has just announced a proof of FLT. Okay, and then all hell broke loose. So, okay, so Andrew Wiles has announced a proof, and everybody thought nobody is going to see it in our lifetime, and so on. And Andrew Wiles had just done, this was really long ago. I mean, it sounds crazy, but this was a problem which was open for 450 years. So at that time, and even now, it's such a big deal that somebody has announced this. And very few people understood what was going on. And Andrew Wiles is not a crank. He apparently had not given a talk for 7 years. He was just hidden in Princeton in a library, and then that's it. He suddenly said, "I want to give a series of lectures," and they said, "Wow, come." So he was in Cambridge. He gave a series of 3 lectures. At the end of the second lecture, this email started floating that something big is happening. Wiles has just started his second lecture, third lecture, and suddenly in the third lecture, he wrote in the corner of the board some corollary, and he wrote the statement of Fermat's last theorem. So he's proved this, and then there was a gap. There's that whatever all kinds of issues happened after a year or so. So you can read the story in very nicely. It's told by Simon Singh in a book, Fermat's Last Theorem, and uh, elliptic functions and elliptic curves played a huge role in Wiles' proof. And suddenly, this area is no longer in the backwaters. And then everybody was just, okay, I mean, what are the problems? Can we use elliptic curves, elliptic functions to solve this, that? So, this whole area of mathematics, which was due to Jacobi and Gauss, which was just there as a beautiful thing, as you saw, big products equal to sums and so on, and this periodic business. So this all came up, and elliptic functions is 2 periods, and it- this is there is somehow relationship between this and elliptic functions. So all elliptic functions written in a particular way can be written as ratios of a finite number of these kind of products. That's the theorem. So that's due to Weierstrass. And that is why this kind of theta product is very useful. And Jacobi considered elliptic function built out of these guys. And this quasi-periodicity plays a nice role. I mean, you want to somehow cancel it. If you take products of it, if you take 2 guys, and I can cancel it. If I take 4 guys at top and bottom, I can cancel the x's which come out. And then I get a periodicity of the kind where I'm replacing x by x cube. So if I replace x by x times 1, then that's 1 period, and x times q is another period. I get the same thing. And if you that certainly makes sense if you suddenly look at x is equal to e raised per 2 pi I tau, and q is equal to e raised per 2 pi I something. Right? So then the product becomes sum, and you get basically you get periodicity and elliptic function. So this is an out of the way remark and story that why this has suddenly come up in modern period. So in fact, complex analysis books of my time never had a chapter on elliptic functions, and very hastily now their second edition and third edition, fourth edition, they've started including a chapter on elliptic functions. All this stuff was very easy to do. It's no big deal, but they didn't do it. That's all. Okay. So it was out of fashion. Anyways, so I do want to prove some corollaries before we go on. These are again very, very classic results of Jacobi triple product identity, and I don't think you will see them ever in unless, I mean, Fourier series is a good opportunity. That's possible. I mean, you may see Jacobi's triple product in a I mean, ideally, if I teach, I would show them in a complex course, but it comes towards the end. That's the problem. Okay, so first is due to Gauss in 1866, and what he proved was and n is going from 1 to infinity, again due to Gauss. 3 is, we already know this. This is Euler's pentagonal number theorem. That's also a corollary. This was 1740s. This we have already proved last time. Another one due to Gauss. This one is 1808, it says. Not sure. It's an earlier thing. And this one is also due to Jacobi, 1829. Okay, so there are these 5 classical results, and I should remark over here. What is this? This is the generating function. This is the generating function for squares, right? So if you take this whole thing and raise it to the 4th power and just compare coefficients of q raised per n, right? So you take this whole thing over here, raise it to the 4th power, then what is R4n? What you're doing is you're multiplying 4 things together. All of them are squares. So this will be the number of ways of writing a number as a sum of 4 squares, right? And you allow for minus n square also. I mean, so you have, say, 2 square plus 3 square plus 4 square plus 1 square equal to something. You allow for minus 2 square plus minus 3 square, so on. So this includes all these different representations because you're taking minus sign too, right? So you have whatever. And this is a classic problem of, this is known as Lagrange problem, that every number can be written as a sum of 4 squares. Okay, so i.e. R4n is bigger than 0 for all n. That's the generating function approach for proving that Lagrange's theorem. So have you heard of this theorem? Yes, no?
Yes, Professor.
So why was Gauss so interested? Gauss was interested because of this. See, this is generating function for squares. This one is generating function for triangular numbers. So there is a famous theorem of Gauss which says every number can be written as a sum of 3 triangular numbers, for example. That has to do with raising this to the 3rd power. And I should mention that Ramanujan considered this one, q times 1 minus q to the k raised per 24, k going from 1 to infinity. I mean, he basically did q infinity raised per 24, and he wrote it like this, and he proved many things about this. So tau of n turns out to be multiplicative. That means that tau of n times m is equal to tau of n times tau of m. And there are many conjectures here. For example, this uh, two Fields medals have gone to proving partly, have already gone on such things on tau of n. So there's more waiting. I mean, there are some conjectures which are of Ramanujan which are still open. If you prove them, then I think you'll be very famous. Okay, Simon Singh might write a book about you if you prove it. So, so these kind of things are very, very classical and very, very central to mathematics. They keep coming up. Unfortunately, when you're studying mathematics, there's so much of abstract stuff that you're supposed to absorb that these nice, simple, beautiful results from the past, they disappear from you. So these are very classical results, and you'll find them here and there, but nobody really. Everybody knows about them, and everybody, they ignore them at some stage until they need it. So Fermat's last theorem was a point where people needed it, and then it showed up. And even now, recently, they've come up with problems. So anyway, proofs. So Jacobi's triple product identity is we'll just write it again. XQ infinity Q over X Q infinity Q infinity is equal to minus 1 raised per n, 2 raised per n, choose 2, x raised per n. Okay, and we sometimes take, so let's call this equation 6 because the other one was 5. And we sometimes take q to the q square and x to x cube in 6. It's a to get an equivalent form. And that equivalent form is x cube q square infinity. X goes, so this is q square, q square divided by x cube, so that again q by x q square infinity, and then q square infinity, and n equal to minus infinity to infinity minus 1 raised per n. And here I'll just, this is n square minus n and then x cube, so this will become q raised per n square, x raised per n. So I had a x raised per n, q raised per n, and then there's a q raised per n square minus n. So this cancels. So this we'll call equation 7. Okay, so what do you do for 1? Put x equal to minus 1, and you get. So when you put x equal to minus 1 here, you will get this sum immediately. So sum is immediate, right? And x equal to minus here will be q square infinity, and then another minus q square infinity, and then q square infinity. So, well, what do you have to note? Well, you just have to note that what is this? This is 1 plus q, 1 plus q cubed, 1 plus q 5, and this whole thing is squared. these two together, and then this is 1 minus q square, 1 minus q4, 1 minus q raised to 6, and this is exactly what Gauss had over here. So n going from 1 to infinity of 1 minus q raised per n, 1 minus q raised per 1 plus 2n plus 1, 2n minus 1, and square. So this is this. For 2, you put x equal to 1. So it's immediate again. So if you put x equal to 1 here in 7, okay. So so in this guy, and then you get this channel. Okay. Now for 3 is Euler. So you put q going to q cubed, x equal to q in 6. So this is 6. So you put q equal to q cubed. Let's just look at this side. So it was minus 1 raised per n, q raised per n choose 2, n into n minus 1 over 2, and x to the n. So this goes to summation n going from minus infinity to infinity, minus 1 raised per n. Q is going to q cubed. So it's 3 by 2 n square minus 3 by 2 n. And then there is a x, so there's a plus n and x to the n. So this becomes n going from minus infinity to infinity, minus 1 raised per n, 3n square minus n by 2 x to the n. So this is your Euler's the sum side. This we already know, the pentagonal number side. And for the other guy, here, so x is qx, right? No, wait, it didn't have any x. This is fine. And for this side, you have q infinity. So q is going to q cubed. Then you have q cubed over x, that's q square, q cubed infinity, and the third one is q cubed infinity. So what is this? This is the first one is 1 minus q, 1 minus q raised per 4. So the base is q cubed. So you multiply each term by q raised per 3. So that's the first guy. Then the second guy is 1 minus q square, 1 minus q raised per 5, 1 minus q raised per uh, what uh, um, 8, so on. And the third guy is 1 minus q cubed, 1 minus q raised per 6, 1 minus q raised per 9, and so on. So ultimately, you get all of them together. So you get 1 minus q, 1 minus q square, so on, which is the same as q infinity. So this is the LHS of Euler pentagonal number theorem. Right? Any questions? Is this okay? Is that fine? Give me a sign of life. There's no sign of life. Are you guys taking a walk or what?
Professor, trying to process this.
Uh,
Same, Professor.
while processing, the you froze all other circuits of your brain, is it? Okay, so all I'm doing is I'm taking these guys, Jacobi triple product identity, and there's one more equivalent form where I replace q by q square. So I get this guy. And then I just put various values. I mean, I could ask you to do them in exercises, but I don't want to bother you, so I'm just doing it. So it's not a very big calculation, but yeah, I mean, you have to start manipulating these products which you are not familiar with. So if I give it to you, it will take you a long time to do. But essentially, you write them out and recognize what they are. Okay, next we take 6. And so now we write, okay, so for the last two, so we take 6 and take, let x replace minus qx. So we get minus qx q infinity minus 1 over x q infinity and q infinity. And on this side, we get n going from minus infinity to infinity, q raised power n square minus n by 2 plus n x raised power n. So the minus sign disappears. And this one I'm interested in writing in a little different way. So what I do is I write from, well, first I just combine the two. So it's n squared plus n over 2 x raised power n. And then I break it, I split it. So it's n going from 0 to infinity, q raised power n square plus n by 2 x to the n, plus minus infinity to minus 1. Sorry, why is it minus sign here? X to the n. Then this one stays the same. And this one I replace it with n going from 1 to infinity. I replace n by minus n. So this becomes this, x to the minus n. So same. Yeah. So, and this is n equal to 0 to infinity, q raised power n square plus n over 2 x to the n. And here I shift the index. I write from n equal to 0 to infinity. So the 0th term becomes 1. So n, this is n times n minus 1. So it becomes n plus 1 times n over 2 x to the minus n. And I've replaced n by n plus 1. So this guy. And then I put them together and write like this. Is that okay? So I'm just messing with the sum and I'm doing this, and then what I want to do, so I get whatever I get, this is equal to this chap right here. I'll just rewrite it. Minus qx q infinity minus 1 over x q infinity and q infinity. So this chap, let me call it number 8. So now what you do is you put x equal to 1. Okay. So this is for this guy. So I've got it almost like this. I just have to get this term. So n plus 1 over 2, n going from 0 to infinity. There is no. So you know what? I think I can even. I wonder if I can copy paste this. Let's try. Yeah, I can do that. It's nice. So I should highlight this. This is what we want. That's it. So you put x equal to 1. This side is okay. You get 2 over here. So you get, well, on this side, you'll get 2 times q raised per n plus 1 over 2, n going from 0 to infinity. And on this side, you will get minus q infinity. You get minus 1 q infinity, and you'll get q infinity. And we want this business right here, and this 2 should cancel. So what do we do? What we do is that, so bring the 2 on this side, first of all. Right? And then what? Then this is minus q. So I'll just write it out. 1 plus q square. Blah, blah, blah. This one is 2, 1 plus q square. So 1 plus q, 1 plus, so first term is 1 plus 1, which is 2, and so on. So same as whatever this guy was there. And this is q infinity, which is 1 minus q square. So what do I want? I want 1 minus q to the 2n. So first of all, this 2 cancels. That's a relief, right? And then 1 plus q times 1 minus q, I will get 1 minus q square. 1 minus q to the 4. So I multiply these two together, or these two, whichever one you feel like. And then I want a square. Do I have a square of that? Yeah, why not? So I have one term more here, extra. So I multiply it by q infinity again, the same thing again, and I'll get a square. And except that I have something now in the denominator. Q cubed and so on. And now I cancel this one extra term. So I've canceled the 1 minus q square, but I have 1 minus q cubed, 1 minus q to the 5, and so on. And that's precisely whatever this guy is, 1 minus q to the 2n, or 1 minus q to the 2n minus 1, for n equal to 1 to infinity. That's the RHS. Is that okay? And now, what we do is, now we need this guy. Now just one remains. So this guy remains. Number 5. Okay, and this is nice. I've just discovered a new trick. So we use this guy again. This we said was number 8, right? So we use 8 again. What do we do? This is not needed. what we do is we divide both sides by 1 plus x and take the limit. So we divide both sides by 1 plus x and take the limit as x goes to minus 1. So what do we get on the left hand side? Right? So assuming that you can do whatever I'm doing right now, I take the limit inside. And then this limit right here, this guy, you can use L'Hopital rule or something and just get the answer, which is what do you get? You get n times x to the n minus 1 replaced by this. So this plus minus n times minus 1 raised to the power n minus 2. Okay. And this becomes essentially minus 1 raised per n minus 1 to n plus 1. So you get n equal to 0 to infinity times 2n plus 1 on this side. On the right hand side, the limit as x goes to minus 1. So you're taking this products minus q, what is it? Minus qx q infinity minus 1 over x q infinity and q infinity over 1 plus x. So this term is the one which is the offending term. So minus qx q infinity. This term you split, you get 1 plus 1 over x, and then you get minus q over x q infinity q infinity over 1 plus x. And again, this cancels and you get a 1 over x, and you place x equal to minus 1. So you get minus q infinity q over x, sorry, q infinity again. And this one was already q infinity. So there you go. The cube. And if you want to write it out, it's q raised per n going from 1 to infinity, and cube. So there's a minus sign here, and here I forgot to put a minus sign, n minus 1. So bring this to the other side, and you're done. This multiply both sides by minus 1. And then we're done. So where are we? Yeah. So what we wanted to prove was this guy. Minus 1 raised per n, 2n plus 1 times q raised per n plus 1 over 2 is the infinite product, 1 minus q raised per n cube. So again, I mentioned that Ramanujan had raised part 24 over here, right, in the tau function. He's looking at this raised per 24 with some q multiplied in front for some reason. And whatever, he doesn't have an expression here. This is a nice expression of Jacobi. So, I mean, it's natural for Ramanujan to say that, okay, we have these nice expressions. What about higher powers? You know, it's an easy question for somebody who's a natural computer to try it out, and he could calculate a few of them, and he found some properties, and then that gave many other people Fields Meadows, Ramujan Ringgit. Okay, any questions? Any questions? Any questions?
Not really, Professor. I think like we'll have to kind of go through it again and like to be able to completely understand the things.
Okay. All right. So yeah, I mean it's a lot to sort of process. There's so many symbols here, and the best way to process would be if I give you homework on this. Then you'll be forced to process. So yeah, we'll see. So this is the number theoretic component which I keep promising. Some level of number theory shows up here. And if possible, we'll try to prove certain things. The point of these identities is that it is required to prove certain other things that we will require. So sometimes it may not be possible to prove things in a purely combinatorial fashion, and then we need to use the analysis to prove them. And you if you do the homework, I think you've seen I've given the assignment, right? Everybody's got the assignment.
Yes, Professor.
So when you see the assignment, there's a lot of programming to do to manipulate these symbols and coefficients so that they become real for you. That's the idea. At some point, that is easy to figure out or check on a computer now, what the numbers are they matching? And then the real math is the combinatorics. Okay, so I'll just remind you of something uh, for our next theorem. So we recall we had paths. We were going to, let's say, mk from 0, 0. So we would go x, y like this, some path like this, right? And the number of such paths was m plus k, choose k. And then we were doing these boxes underneath, right? The area underneath. The area would keep track of how many sign changes were happening and so on. So we had the area underneath. And this was, once you keep track of the area, then you had some kind of a Q binomial coefficient. So this was the generating function of these boxes or area. So Q raised by the area of a path. Remember this? Q binomial. So what we want to do is we want to flip this picture and do a complementary picture. So when you do a complementary picture, so suppose you have this as a path, right? So the complementary picture would be that you take these boxes. Right? So you keep track of these boxes, and what are these boxes? These boxes are Ferrer's diagrams. So what you do is you consider um, the generating functions of partitions of n with so partitions which fit inside, uh, let's say, k by m box, or what is the same thing, less than equal to k parts and each part less than equal to m. And then take this generating function over n, and this is your m plus k, uh, k, right? So this we had looked at the area underneath, but if you look at the area above, it's by symmetry. I mean, you'll have some path which is exactly the opposite. By symmetry, it's the same thing. And if you look over here, at this point, if you look at this, just put it by dots, then this is some kind of a Ferrous diagram or a Young diagram, right? So it's the same thing. It's the same area. And we had earlier, I think we had just done it something like this: paths from 0, 0 to, and got n choose k directly. But one could do it this way too. I mean, it's the same thing. Just do this plus this over here. Sorry, this was n choose k, and this was n minus k k, and this was, so this was in the first couple of lectures that we did this Q binomial business. So just to remind yourself, my suggestion is, so just work out again. I mean, this you're done in the first homework, but just list once for to figure out what is 4 2. So what you have to do is you have to go from here to here, here, here. So just 2 2, right? You just have to go from 0 to 2. So this is one. So this will give you an empty partition. This will give you this partition. Right? And you work out all of them. And then depending on the partition of n, so what you know, number of boxes. So basically it's the partitions, the number of partitions of n, and this Q binomial coefficient comes up over there. So our goal is, so a goal is that we'll prove some identities, prove some finite forms, extensions or forms of, say, Euler's theorem. And there is a theorem of Sylvester in particular that I'm looking for. So Sylvester is a very active person in this, was a very active person in this domain. And he has a theorem which we want to prove. And also I have some further hope of being able to cover symmetric functions because I found a book. So, but I have to read it first. I found a nice book on symmetric functions. So, let's see if we seem to have a lot of time. I mean, I've realized this 1.5 hours business is quite a lot. So one can cover a lot of stuff, but it's not necessary that you will be able to do all of the stuff yourself. But I mean, on Sage and all these things are easy to do. So we can cover some of this stuff if possible. But we are in terms of, I would say we are one from Hardy and Wright. We are maybe 1 or 2 theorems short. And one of them is really complicated. I don't know if I'll cover the proof of that. But Hardy and Wright, their book on partitions, they cover exactly what we have been doing right now. So you can read it now. I mean, it's good to read this book. Just look over and see what, familiarize yourself what it contains. If it contains the same things done in a different way, it will probably make you feel good that you know this stuff. And um, we are still the, I don't know, this Jacobi part, I don't know whether it's there in the book that I mentioned. So yeah, this is from various sources. Anyway, basically you'll have these the partitions which fit inside this. So these are K and these are M. So the partition will fit inside here. So it'll have less than K parts and each part has to be less than M. Right? So suppose you have a path here. Uh, suppose you have this path. Right? Then you only have this partition 2 plus 2 plus 1. And suppose you have this path. Then you'll have this partition 1, 2, 3, 4, 5 plus 2 plus 2. So does that answer your question? So both these conditions have to be satisfied.
Yes, Professor.
And yeah, whatever n is this is what the partition is. I mean, you count the number of boxes. So earlier you were counting the area. Area is the same as number of boxes. So it's just that it so happens that we instead of counting downstairs, we're counting upstairs. That's all. So, well, there were some symmetry properties which we did. So any other queries?